Okay, good. Okay, so let's start. I want to first make the key announcement. There's not going to be a lecture on Monday. So, just study for the exam. I find a Monday lecture with a Tuesday exam just doesn't work. So we're just gonna. If we find ourselves that we have like more material we want to talk about, we'll just like use the first Monday lecture of RR week to talk about other stuff. So don't worry about missing out on material. Office hours today are 2:58 Corey. After we're in this room, just from 10:30 to 11. The reason is I recommend this talk today. In 310 SDH, which if you don't know is the building basically across the street. So that starts at 11 today. So that's in person only, not recorded. So you don't have if you want to attend it, you really have to go to it. So I'll just walk over from my office hours to the. So again, reminder, the exam is Tuesday, 7 to 9 p.m. Details on Ed. Remember, one sheet of notes, handwritten notes. So we were a little concerned so either people found the homework this week super easy, which is fine, good for you, or the people haven't spent as much time on the homework this week because we found that the attendance at the homework parties yesterday and the day before wasn't that high. So remember, this homework is fully in scope for the exam. Okay, so we'll release solutions, but you really should understand what's going on in this homework because it's on the exam. Okay, so just making sure people know that for scope. To the extent that today I'm talking about autoencoders, which are on the homework, those are also in scope. But if I get a chance to start into transformers are not in scope. Okay. So the topic today, we'll talk more about autoencoding and self-supervision. And then if I can, I'll start into transformers. And however far I get is fine. The lecture a week from now will definitely be hitting transformers. And the homework next week that we're going to give is basically going to be redo the midterm plus a short problem or two. So you don't have to worry about not being able to do it, given that you'll have also all the spring break. So this is the goal. So recall last time, we talked about PCA reinterpreted as self-supervision. Via an autoencoder. So let's talk more about this in sort of we didn't have quite that much time last time. So if you remember, what we said was that standard PCA formulation for dimensionality reduction so recall the standard PCA formulation for dimensionality reduction is you have a bunch of data, X train, which I'm just going to think of in column form, x1, x2, xn. So this is n. These are d-dimensional vectors. You have this, and you can, so I'm not going to worry about the removing of means part. You can just think of that as an exercise for you about how to think about the removal of means parts. Maybe I will talk about it in a bit just to make sure you can understand it. But so assume for now means have been removed. So then you say, you look at X and you say this thing is U sigma V transpose by SVD. Where this thing, right, this, so yeah. I'm switching from what I did before. What's the size of this and what's the size of this? So by full SVD. Okay, how big is this U matrix in this case? D by D, exactly. And this is N by N. So I'm switching the order from, switching things from last time. Sigma, right, is the same shape, and this is diagonal. Sigma 1, sigma 2, okay? So once you assume the means are removed for standard PCA formulation for dimensionality reduction, we say that we're going to use the big singular values. We're going to say that's where the action is, and we're going to use the singular vectors corresponding to the big singular values to do the projections. So in that case, in this case, it becomes we're going to project onto U1, U2, up to UK, where K is the number of dimensions you want to keep. K less than D. And that's how we do dimensionality reduction. So this is an unsupervised method because you don't have any labels, you just have inputs X. And it proceeds by this calling of the SVD. Okay? So last time we said that we can also think of this as actually what's the interesting thing we want to get? The interesting thing we want to get is this subspace. Interesting object. So you have interesting subspace you want to get. So we know that this is the subspace by Eckert-Young, which minimizes the reconstruction loss for the matrix X in Frobenius norm. So we can think of this as minimize X minus W1, W2, X. In Frobenius norm, we minimize argmin over W1, W2, where W1 looks like this. sorry, this is going to be, I could written it backwards. W2, the thing that acts first, is going to take d-dimensional things. Okay, I should really write this in a consistent way. The first thing that acts takes d-dimensional vectors and maps them into k-dimensional vectors. And W2 takes k-dimensional vectors and maps them back into d-dimensional vectors. So in this case, the interesting object is, you can think of it as because I'll ask you, what corresponds to the subspace spanned by these k vectors? Let's just work it out, because I think this is a source of some significant confusion. So I want to make sure you understand the slight subtlety here. So first, I have these two things. So any questions so far, right? We said that because of Eckert-Young, this thing, right, this is a way of representing rank at most k linear operation. So a rank at most k linear operation that takes linear operation mapping RD to RD. Right? Because d-dimensional things come in and d-dimensional things come out. So this entire operation is some linear operation that maps X back into dimension D, but in a way that only preserves a subspace of size K. So this is like a projection of some kind, right? And so this is saying that this is the best rank K projection of the entire matrix X in Frobenius norm, which you know by Eckert-Young has to be minimized by projecting onto this subspace. Right? So that's what we talked about last time. But now let's get into the details a little bit. And this is a source of some confusion when it comes to autoencoders and self-supervision and learning representations. So let's make sure everyone understands it. So I said here that one way of thinking about what's interesting in PCA for dimensionality reduction is the interesting object is the subspace spanned by these things. Because that's the subspace you're going to keep. Right? So what is the corresponding object over here? So let's call this subspace spanned by, right? So call it S interesting. Okay? Which is the span of U1, UK. So I want to know over here, on this side, what is S interesting? So first, does everyone understand the question? It's kind of really important that you understand the question and why we're doing this, right? We want to, because last time we said that, okay, this is actually the same as this, but now we're going to go in more detail of what does it mean to be the same, right? And what's actually might be a little different. Okay? So pause for a moment. Who has a question about what we're doing? Anyone? No? Okay, good. So now I'll ask the question. S interesting here is the span of these first KU vectors. What is S interesting here? Raise your hand if you know the answer. I won't call on you yet. Just raise your hand if you know the answer. So I can kind of gauge who knows the answer. I'm not going to call on you just because you raise your hand. Okay, now put your hands down. Raise your hand if you do not know the answer. Okay, that's the majority of people. Raise your hand if you're not sure. Some of you are not sure. So you actually kind of know, but you're not sure. Okay, so In the interest of time, I want to not just give you time to work it out, but I do want can someone volunteer for a hint you might want to give to somebody who doesn't know the answer of what something that they might want to think about? Yeah.
I would think about the video.
Okay, so one potential hint that is being talked about is maybe you should think about, so over here we did an SVD. This is something that we talked about last time. We can do this minimization because I can also make this 1 over n. It doesn't change the minimization, right? So I can do this using SGD, so there's no need to call any SVDs over here. But for insight, you might find it useful to think about SVDs over here. And so that might be a way to proceed. Okay, that's one way. But I'm going to put that aside for a minute. Does anyone have a potentially easier hint that you might want to give people? Yeah?
Maybe, so think about from W1 and W2, which matrix reduces the dimensionality of your data.
Okay, so one other hint might be, think about W1, W2, and see which one is potentially reducing your dimensionality. That's also useful as a way of thinking, but a little bit tricky and subtle, which is what we're going to get to in a moment. I'll give you another hint, okay? If you wanted to write S interesting as some kind of span, what size do the objects have to be whose span you're taking? Okay, so let's just do that together. This is a subspace of what? It's a k-dimensional subspace because it's a span of k vectors, right? That's clear. But what is the space it lives in? It's a subspace of what space? RD. So this is RD, right? Because all the vectors here live in RD, and we're projecting into something which is still, you have to project into a subspace of the same thing, RD. So what are possible d-dimensional vectors that you have over here? So the columns of W2 are d-dimensional, and the rows of W1 are d-dimensional. So you have two possible things that are both d-dimensional. Okay? So now let's work out what happens a little bit. So if you were to use these vectors to do a reconstruction of the original training data, except projected onto this subspace, right? What you would get is something that lies in the span of these things, right? That's what it means. So when you run this operation, whose span do we live in? Like when you run this, right? We want to be here, but there's operationally, if I just initialize W2 and W1 to something, what does this linear operations output lives in the span of what? Yeah. So you're reconstructing back to, just as it was stated, you're reconstructing back to RD using W2. So the interesting object here that corresponds to this object is actually the column span of W2. Right? Just formally, right? It has to be, that's the object. So this makes us, this brings out something which is a little bit subtle in self-supervision, right? Which is, what is the role and interestingness of encoders and decoders in the context of self-supervision, okay? So you come back over here. When you actually use standard PCA to do dimensionality reduction, right, you keep a k-dimensional vector, right? So the interesting object in one sense is this subspace, but another interesting object, right, an interesting operation is, let's say UK is the first k columns of U, right? Is UK transpose acting on something? Because this is what returns k-dimensional vectors. Is that clear? So when you think about dimensionality reduction, the object, if you're going to use this as a, if you do PCA on a bunch of data to learn a dimensionality reduction, which then you're going to use for a downstream task, like classification. So I have like a bunch of unlabeled data. I want to I have a linear model I want to use on it. So I have a bunch of unlabeled data. I have a very small amount of labeled data for a particular classification task. I can use the lots of unlabeled data to learn a dimensionality reduction to 3 dimensions, let's say, and hope that I can now fit, using the very small amount of data, a good model on 3 dimensions. Right? That's how you use it, right, in classical ML. So the other interesting object is the subspace, but another interesting operation is UK transpose X. What is the corresponding operation here? Here, it's clearly W1 acting on X. Because that's the thing that returns a k-dimensional vector. Is that clear to everybody? Okay, so this is bringing out a little something that's interesting, okay? What you would like at optimality, right? At optimality, when you actually do this minimization, you would like to see the columns of W2 having some alignment to the rows of W1. Because you only want to capture what's actually happening in this subspace, right? Because if you capture anything else, that other stuff is suboptimal. It'll pass through into your reconstruction in a way that's not what you want. That's not the dimension you want to keep. So at initialization, these two might be, completely unrelated to each other. But at optimality, it better be that these columns of W2 and the rows of W1 have some kind of alignment to each other in terms of hitting the same subspace. However, you notice one thing. Over here, because we did the SVD, we have the guarantee that each of these are orthogonal to each other, and each of these has a unit norm. Right? That's just a part of the guarantee that the SVD gives you. Over here, when we're doing this minimization over these matrices, we are not asserting this in any way. Okay? So we're not going to assert that, for example, the rows of W1 are orthogonal to each other. There's no such guarantee that we have. Nor is there any assertion that the columns of W2 are, have norm 1 or are orthogonal to each other. But it doesn't matter, right? Because at optimality, it better be that this thing at optimality, meaning at optimality of this I don't know, call this loss, right? Optimality for loss, W1x should be capturing exactly the relevant subspace of X. Or let's call it the relevant degrees of freedom in X. Does everyone understand this? So degrees of freedom in the context of linear is just dimensions, like individual directions in there. Okay, So this is often a point of some subtlety for people to understand. Okay, so when you do, if you wanted to use this thing as in the same way to do dimensionality reduction, all you would do is use the encoder W1. So the way this is often drawn to help you understand these shapes is we draw this as saying, so I'll draw a little picture here. Picture. X comes in. Something is encoder, which is W1. Takes it down to k dimensions. And then I have a decoder that comes back up to d dimensions. And out pops x hat. So we often draw it this way to emphasize that we're squeezing it down in size. This is just a representation of this operation and these matrix shapes. So if I say this is a linear layer that does this, and then this is a k-dimensional representation. Here. It's sometimes talked about as, you call it like, you want to find the k-dimensional latent space where you've distilled out all of the information. So this is one perspective on what's happening. So this is the like squeezing down to the extracting the core information perspective. There's another perspective on this as well, which you might not have heard about, but it's also useful to think about. So you can also think about what is the status of the full reconstruction, W2, W1x, right? That would be like taking the data and projecting it down onto this subspace. So if you remember, probably when you learned, so tell me if this is true, when you learned PCA in your machine learning class, did you learn it in the context of saying, for example, suppose you have data that's actually coming from a low-dimensional space, but has noise added to it in all of its dimensions. Did you see this example? If you raise your hand if you've seen this kind of motivating example for PCA. Okay, some of you. Raise your hand if you did not see anything like this motivation. Okay, so it's a useful way to think about it because it also gives you a way to interpret what's happening. So if you think about your underlying data as being, so aside, suppose the backstory of your data is k-dimensional physical reality, okay? Something underneath, real life, physical, some physical thing, right, that you cannot see that is actually k-dimensional. Then you have D different noisy measurements of reality. Okay? Each of which is a linear operation on reality. Different noisy, quote, scalar measurements, each of them is a single real number, is a linear operation on reality plus independent measurement noise. Okay, think of that picture of what's going on. Does everyone see this as a very natural picture to think about? You have something real, you're going to measure it. All you have access to are the measurements. Your measurements are noisy. They are what they are, they're noisy. So now you look at this thing and you say you'd like to get back something which is kind of representing this physical reality. What's it gonna look like? Right? You're gonna hope, one hope you're gonna have is that the signal that's coming through here, through these linear operations, is actually stronger than the noise. Right? At least overall. It better be that case. It could be that individually, any individual measurement is too noisy, but then redundancy across the measurements better give you access to that signal. Otherwise, you're screwed, right? You see that? Like, it's kind of just basic. Okay, so you make that kind of hope. Then you say, what does this look like, right? What is the covariance structure of this thing going to look like if this thing has a covariance structure? What it's going to look like is you're going to see the covariance structure of this thing with another. Suppose you make all of these independent measurement noises IID. For simplicity, assume IID. You're going to see something whose covariance structure is going to look like this. Okay? Signal plus noise variance. Second dimension of signal plus noise variance. Signal 1, signal 2. Signal k plus noise variance. And then you'll see noise variance, all the way down, noise variance. Right? Why do you see that? Because adding IID noise means in every rotated coordinate frame, it's still IID noise. So this is a linear operation. So the covariance structure is going to be of independent things. There's going to be a superposition of those two. The covariance structure of this thing is just going to be the signal structure. And then zeros everywhere else because it's only k-dimensional. And that's what you get, right? So now you look at this and you say, great, if I project onto just these k dimensions, where I draw it here, I will get all the signal stuff plus whatever little bit of noise there is in the kind of each individual measurement. That's hope. I can't get better than that, right? And then all of this noise will be rejected, right? So that's like another way of thinking about like where does PCA come from? Like a backstory. It's always good to think about this. Whenever you have an algorithm, it's useful to have in your pocket what is the backstory of reality for which this algorithm is sort of optimal. Good exercise to have in your mind. Like, when does this make sense to do? Questions? Yeah.
So if our estimate
Yeah, great question. So if the reality was this way, and you actually took something less than k, right? You cut it, you would lose a chunk of signal. Right? A useful set of signal dimensions would be lost. If you chose something bigger than k, you would get some more noise. It would also come through in your representation. Okay? So this is kind of a picture. So in this picture, when you do the corresponding thing to W2, W1, which is what here, right? So projecting onto this is just UK transpose, right? That's the operation that does the projection. When you're projecting onto unitary matrix, onto things that have orthonormal columns, you just do that, right? Because this is the representation into k dimensions. To come back, you apply it on UK. So this operation, this is d by d matrix. What is this thing doing? That's the same thing that this is doing. Okay? So another way to think about the operation here is as a denoising or a purification. Okay? So you can think of what you're learning with an autoencoder with a bottleneck is a kind of purification or denoising. can interpret W2, W1 as a purifier or denoiser. So it takes things and it makes them cleaner. Okay, yeah.
Why don't we use directly that W2 is the transfer or is the alignment of it?
Great question, and I'll go into it in a bit. Right, so everyone heard the question? The question was, look, the classic way of thinking about an autoencoder says, I just want to have a rank at most k linear operation. By Eckert-Young, I know that that will give me what I want. So I just set it up as two separate matrices that have nothing to do with each other, set this up and say, great, let me just do optimization on this. But the question was, I actually know more. For example, I actually know that one is the transpose of the other at the final solution that I want to get. So can I do that, right? Can I rig this up to say, to enforce that constraint, for example, by using weight sharing, right? To say, I'll just enforce that there is a weight sharing relationship between these two, and then do it. And the answer is yes, you can do that, right? However, it's an interesting question to see if you do that, will it work? Right? And again, you have to make the distinction between could it work and will it work? Right? That's always the interesting thing that's like different in deep learning versus standard ML, right? So could it work? Of course it could work because you have a possible solution right here. You know it exists. So there is an optimum that exists for that problem. That problem, if you enforce that weight sharing, actually has fewer parameters in it, right, than the other one. So it's like even a more compact representation. It's fewer parameters. From a traditional ML perspective, it might be much better. Then the deep learning problem is, will it work? And that requires you have to understand what the character of that optimization problem actually is. And so I think it turns out that if you do that and you try to do it, sometimes it'll work, but sometimes it won't, because you get stuck in a local minimum, because as we say, products of things in this loss is definitely non-convex in these parameters. So this is this issue that we say in deep learning all the time, which is if you have too few parameters and you have non-convexity, which you always have non-convexity, whenever you have anything deeper than one layer, which is here we have two layers, right? In that case, you will see the possible bad phenomena that come from having this non-convexity will actually show up. And you'll get the problem of having local minima and things like this can actually happen too. So you have to be more careful on doing it. When you do it this way, you have lots and lots of extra parameters in the system, which basically, in effect, makes this problem will actually solve. Like when you run gradient descent on it, it'll work quite reliably. So it's an excellent question. Okay. So you can. So yes, just enforcing the transpose is not necessarily a good idea. Yeah.
So I use W2 and W1, which are pretty unrelated. Will the result be that one is just together in the end, or?
Okay, that's a great question. We actually give you a homework about it, right? I think it's this week. It's on the homework. So the question is, if you actually do it and you say, let's just run it and see what happens, like what actually happens. So if you just did gradient descent on this problem and said just optimize it, will you get things that are transposed to each other? No, you will not. Okay? There's not a strong enough inductive bias to pull you to have that happen. What the homework problem, which was an old midterm problem, says is that if you then added a regularizer that was quite small and penalizes the Frobenius norms of these two, then it would have a pull towards having that happen. Because you need something. So you need something that'll make this matrix kind of try to be as small as possible, right? Because that's what will give you that big. So wait, look, if this is big, multiplied by 2, this has to be divided by 2 to have things work out at optimality. So you know that whenever you do that, overall the numbers have gotten bigger. Because multiplying by 2 makes things twice as big. Dividing by 2 only makes them half smaller. Right? So you need to penalize, something that makes that happen. So you need something like that to have it go there. Yeah, it's also, okay, here's the question since the exam is coming up. Oh man, okay, I'll be fine. Like, for the exam, suppose I started this at 0 initialization. I do 0 initialization. Remember, for many least squares problems, we say start at 0 initialization, and it's like totally cool, right? Suppose I started this at 0 initialization. What will happen to SGD if I start this at 0 initialization? So this is the 0 matrix, and this is a 0 matrix. Backprop. What happens? Take a minute. Okay. Has everyone had a chance to think about it? So first, I want to make sure everyone understand the question, right? Okay, if anyone's not understanding the question, raise your hand, please. Like, I don't want everyone to be confused, right? So my question is, what happens if I start at 0 initialization and start running SGD or gradient descent on this problem? Okay, now, does anyone who feels like they know what's going to happen if I start at 0? Raise your hand. So I need a loss, right? So the loss here, when I do, when I write Frobenius norm, 1 over n Frobenius norm squared, that's just squared loss. That's a standard squared loss on every column of x, right? So you have a clean loss function. So when I do SGD on this or gradient descent, what I'm saying is I take x hat, I put a loss layer afterwards. And that loss is squared error. And I'm going to take the gradients. Okay? So backprop. Anyone want to volunteer? So who's confused as to what will happen? Like, you have an exam. Okay, exam is written. Like, you can. If you're confused, it's fine, right? I don't no sweat off me, right? Yeah, you get a 0 gradient, right? The reason you get a 0 gradient, so you think about each parameter, right? On the parameters here, you'll get a 0 gradient. Why? Because the loss will say, please make this bigger, right? And this will say, but my inputs are 0 and I'm multiplying them by something. I cannot make them bigger at all. I have no gradient. My gradient is 0. No matter what I do to these parameters, the output will be 0 because my input is 0. Okay? So my gradients will be 0. And then I'll backprop here. And this will say, do I need to do anything? No, I do not. I have no gradients. So chill. So this will stay, and this will stay at 0 forever. Okay? This is why you learned Xavier and initialization, right, in the context of deep learning. For a single layer, it's not a problem. You can initialize at 0, and everything is good, right? But when you're not a single layer, you can't initialize at 0. Like, bad things happen. Okay? You just don't move. Okay, anyway, so this came up in the context of saying, once you've initialized these somewhere other than 0, it's kind of tricky to think about like what's going to actually happen to all this. Okay. So I want to make sure we understand the core ideas of autoencoders generally and self-supervision. So it's called self-supervision because I generate the problem that I'm doing from my data itself. I come up with my own label. So in this case, I set up the problem, I set up the architecture, the encoder-decoder architecture. And what does that mean? It means I've created a problem, which is come up with an x hat that's like x, right? By setting it up as an encoder-decoder. And then I say, what I want to do is I give you a label, which is x itself. I wasn't given any labels to begin with, but I make my own, which is I just take the input and call it the label. Now I have a loss, and I can train. That's why it's called self-supervision. But I train it the same way I would train any other supervised learning problem. So we can use nonlinearity too. So in general, you can take x, and you can stick anything you want inside this encoder block, including nonlinearities, as long as you get down to something. Here, okay, encoder block, network, could be deep, have nonlinearities in it. And then you can make a decoder block. Encoder network, call this x hat. I stick it into a loss layer. X hat, x. So I just take my fake label, x, for the task. And then I can still do this. So if you think of it this way, it's like PCA seemed to work in practice. We can interpret it in this way as an encoder-decoder architecture. And this is a way of dealing with linear models. So let's just do the same thing for nonlinear models. And just hope that everything works and works at some reasonable level. So this is a way to get self-supervision using these. So what's happening here? What's happening here is that you might think that, wait, if I'm just learning a giant network, right? The whole thing is some big network, right? This is some big network. Everything in here is a learnable parameter. A d-dimensional object comes in, and a d-dimensional object comes out, and I want to minimize squared error, for example, or anything else, any other loss I want. If it's anything that's sort of a reasonable loss, it will be minimized if I could emit x itself. Right? Do you see that? Most losses, if I have x itself, I'll do as well as I could possibly do. So this thing wants to learn the identity. You see that? Like, it would like to learn the identity map. So why doesn't it learn the identity map? Like over here. Anyone tell me? Like, why don't I actually learn the identity? Yeah. Okay, that's a great, so let me expand that out as the answer was it can't learn the identity because it has a choke point. There's no way to get, in the linear case, to get everything through. Right? There's just no way to have, you can't represent the identity as a product of two matrices like this. There's just doesn't exist. Okay? This becomes trickier in the context of nonlinear mappings. Right? So if you've never seen it, a side exercise. Is there a nonlinear mapping from R cross R to R that is invertible by a nonlinear operation? Has anyone seen this problem before? If you've seen this problem before, as stated, raise your hand. Problem is there a map that takes two real numbers into one real number that you can invert to get back the real numbers that you started with? Okay? And you're allowed to do anything you want. It's nonlinear, right? So that means everything. Linear just means not restricted to be linear, like any operations you want. So most of you haven't seen this. Okay, so now let's just you should do this, but how many people think that such an operation exists? If you want to make your life simpler, you can think of, instead of R and R, just think of the unit interval. Like, think of your data is coming from the unit interval. So you can if you want to, you can just think of it as 1 cross 1 and into the unit interval. So can you map a square into the unit interval such that you can get back the square? Okay? So how many people think you can do it? Raise your hand. How many people think you can't do it? Raise your hand. Kind of evenly split. So I'll say, anyone who wants to weigh in on the can't do it side? Like, why do you think you can't do it? Yeah. Okay. Question is, maybe you can't like fit it all in. Like, the cardinality is different. So then you say, oh wait, what's the cardinality of the number of points in the square? It's countable infinity, uncountable infinity for reals. What's the cardinality of the interval? Uncountable infinity. Right? So the cardinality of these two is actually the same. Right? So that doesn't work. So this is all in response to what you said about entropy, because it's like actually subtle, right? Once you start talking about nonlinear. So actually, there are mappings that can take a pair of real numbers on the unit square to a single real number and then get back the original. If you want to, here's a way to think about it. Easiest example. I'll just describe it in brief. Write the number in binary, infinite string. Write the other one in binary, infinite string. Okay? Dilate them. Okay? Then do that. Then back. Okay? You see, I described it to you using my hands, but it's like it should be unambiguous what I just did, right? Because I don't want to spend the time, right? So there is a mapping that will do this. So just the fact that you have a bottleneck for nonlinear operations by itself doesn't tell you you can't do the identity. Okay? However, the fact that these nonlinearities are, have like bounded Lipschitz constants and stuff like this is what blocks you from doing it. But it means that you can, just because you have a bottleneck doesn't mean you can't be particularly contorted in trying to become like the identity. So regularization ideas generally do matter in autoencoders. Okay? Good. So that's the first kind of comment here. It's like a warning based on the questions and discussions in class. So what I wanted to talk about was that I can do a lot of stuff, but I'll skip all this. We have at our disposal the full gamut of regularization ideas, plus more. Okay? So what do I mean by this? So I just told you that just because you've created a bottleneck necessarily doesn't mean that it might not do weird things. Okay? Because I just told you like there's a bounded Lipschitz and everything, but like that might not be enough to stop it from doing weird things. okay? So you have lots of other things you can do for regularization. You can have weight decays, you have explicit regularizers, you also have data augmentations, which are your most generic form of doing regularization. I guess the most freedom you have is data augmentations. So you have to think about, why do I say plus more? The reason it's plus more is that you have another entire degree of freedom that you don't have in traditional supervised learning. Because in traditional supervised learning, what you're trying to do is to solve a particular problem, right? There, you have a limited amount of freedom in choosing the loss function you're going to use for that problem. So it's classification. You could say, well, I'll use cross entropy, or I could use squared error, or I could use hinge loss. You have some freedom, but it's still classification. You're restricted to being within that. When you start talking about self-supervision, the only reason to have this loss function at all, and the only reason to have this label, and the only reason to have this problem is to learn something that's a good representation here for downstream tasks, right? We're trying to do dimensionality reduction of some kind. Or alternatively, you don't necessarily have to think of it as dimensionality reduction. You're trying to do purification or denoising. Or I call it purification instead of denoising because denoising makes you think it has to live in the same space. Purification just means you want to like pull out the essence of it. So like a flower to a perfume, right? It's like you want to capture the essence of the flower appropriately. It doesn't have to be flower looking. And you don't have to achieve perfect purity. Like maybe you're trying to do a flower to its essence, and there's a particular chemical compound that you really want, or particular, but you know what? A few other things is fine, right? It's still going to smell like that. So you should take this more broader perspective to help to understand what you're trying to do. So the only purpose of the loss and the label is just to drive this to be a good representation, which means you have an additional freedom to choose the problem itself. You can choose. You don't have to do squared error. You don't have to do regression. You can do classification. You can do some combo thing. You can do anything you want. So you have a lot of freedom to get this thing to work. So data augmentations are a good frame to think about, because it's easy to think about them. So that once you think about data augmentations, given the homework that we've given you, you already instantly should think of one that you can do, right? So you want to make it so that you're forced to do some kind of purification, right? So one way to force purification is to introduce impurity and force it to be gotten rid of. Then you can't learn the identity. You see that? Because that would be, identity would be the wrong answer. So the first one to think about is called the denoising autoencoder. Which is like paradigmatic. So what you do is, instead of taking x in, you take x plus noise, and you feed that into the encoder. And then this is x hat, goes into a loss. And then you have access to x, right? So you can just use x itself as the target. Does everyone understand what this is doing? So instead of running the encoder directly on x, you run it on x, a noisy version of x. That forces purification, hopefully. Hopefully forces representation to have some purification. So why do I say hopefully? Because, you know, you're hoping that as you train this network, that it doesn't just say, actually, I can just keep this noise all the way through to here and just do the denoising at this part. You're hoping it's going to do it gradually. And the fact that you've kind of put it, you just hope that it does it kind of gradually, right? That's kind of it's a hope. Because the noise you've added is kind of very, so this is where the entropy ideas come in. The noise you've added is kind of very rich. And you figure that it's going to have a hard time keeping this amount of richness through this system. Okay? But the other interesting thing to keep in mind here, though, is that once you've set it up with this hope, the original source of the hope, your real source of the hope, is that you're probably going to take care of the denoising in stages as you go through. Tells you that actually you no longer have to worry about whether this is actually squeezed down or not. Do you see that? Because now, before you were counting, in the linear case, you're counting on the squeezing down as preventing the identity. Once you have nonlinear, even squeezing down doesn't really prevent the identity if you allow any operations. But you still hope that some Lipschitz or some kind of restriction on these nonlinearities will keep it from being it. But you're still not really that sure. So you're already counting on regularization. But once you go to denoising, then identity is not a good answer. So once identity is not a good answer, you're really not worried if this is squeezed or not from a perspective of what you're trying to do. Like even if this was going to be, if x was d-dimensional and this was 20 d-dimensional, right? Even if this was 20 d-dimensional, it's still likely to be purified. It might be an expanded purification, like a lifting that's already purified, but it's fine. You want to use it for a downstream task. So here you have to keep in mind, what is it that you need in the downstream task? Do you need does the downstream task need to have a low dimensional representation, or does it need a purified representation? But most cases, what it actually needs is a purified representation, not that pulls out the appropriate essence. It doesn't actually. So you don't have to think about autoencoding architectures necessarily as having small dimensions here. Okay? So denoising is one. So once you've kind of accepted the fact that you can do denoising, you can now also think about other kinds of noise that you can add. It doesn't have to be additive. Like, what's so special about plus, right? So you can actually have generalized denoising autoencoders. Some box. There's one particular kind of generalized denoising autoencoder that is quite useful in practice, and that's called masked autoencoders. So what do I mean by a masked autoencoder? What I mean is what I want to do. So if you think about adding noise, so for those of you who are undergrads here, right? For those who are undergrads here, you've taken a course called CS70. In CS70, you learned about error correcting codes. And you learned about two different kinds of error mechanisms that could exist. You could have an error mechanism in which a symbol was replaced by another symbol, possibly by adding noise. But you also saw another kind of error, which is a symbol was simply erased. It was simply replaced with erased. Okay? This is very important in practical comm systems and the like real life, this happens. So you can think about the counterpart here. So what you want to do is you want to say, suppose the original x was 1, 2, 3, 4, 5. You want to send in a special, like let's call it x tilde, right? You want to send an x tilde that somehow represents 1 question mark, 3, 4 question mark. Like I just erase those. I mask them out. I say not present. Okay? So If you do this, then your loss wants to get everything right. Or you can just say, just get the masked ones right. Okay, so let's go back to the linear case. Why is this possibly useful? Wait, does everyone understand the problem? It's like filling in. Yeah. Great question. The question is this like doing dropout on data? Yeah, it is like doing dropout on data, but there's a little bit of a subtle issue, which is it's like doing dropout on data, but what you want is actually the effect of saying question mark. You could try to get question mark effect by putting 0. Classic dropout would put a 0 somewhere. But you don't have to just put a 0. You want the effect of putting question mark. So you could, for example, so there's many different ways of getting the effect of question mark. One way of getting the effect of question mark is to actually send in an input represented as, how do you represent something that's masked? I could represent it as 1, 0, 3, 4, 0. That's one way. That's the dropout way, if you were thinking about it, as replacing with zeros. Or I could represent it as a pair. 1, 3, 4, 1, 0, 1, 1, 0. This is the mask, or the one where the zeros are. Like, ignore this. And then you could put random gibberish in here. It's a problem. Like, you have to send in a real number, right? Like, that's the problem in deep learning. You can't. There's no question mark symbol. You have to put a real number. So you can put real number 0, or you could put random junk and 0, or you could, in other problems, you could lift to a higher dimensional space and put in a special symbol that means nothing here, instead of having to do it in two ways like this. But there are many choices of how to do this. The important thing is the idea of masking. Okay, so going back, let's just go back to the data. By the way, data X. Suppose your X data is such that it has a singular value decomposition. Your original X has a singular value decomposition that has some strong dimensions in it. Okay? So if you have something with strong, suppose there's 2 strong dimensions, which means this data is basically 2-dimensional. Okay? There's 2 different ways qualitatively for things to be low-dimensional. They can be low-dimensional in an axis-aligned way, which is that actually there's a couple of numbers here that are actually really big and really important, and all the other numbers are small and near 0. You see, that's a way of having a 2-dimensional subspace, an axis-aligned subspace. That's kind of that's a subspace which does not respond well to masking. Because if you mask out the critically important piece of information, you aren't going to get it back. Or you could have masking that's not axis-aligned. You have a problem where the data is not axis-aligned in terms of where the subspaces of interest are. In that case, you can basically take a matrix and say, look, here's a matrix, and here's a bunch of missing entries in this matrix. Fill them in, such that it's approximately low rank. Right? This is called the matrix completion problem. It's very important in the context of things like recommendations and the like type problems. But you can do that. The same low-rank structure lets you do that. Right? How would you do it? For example, you'd say, well, if these vectors are long, you'd say, let me try to use the entries I do have to project onto representatives of the dimensions, and I can just do least squares and reconstruct everything. Okay? So I could spend more time talking about this, but you wanted to understand, the important thing is for you to understand the idea. Okay? Now, I wanted to make one comment, though. If you do masking, you actually don't even have to restrict yourself to this particular architecture, okay? Where you have noise coming in that is then removed for the reconstruction, and we treat this being blocked. If you can interpret the operations that are happening here, you can actually use them, for example, for masking, you can use what you know about what's happening inside to actually alter what's happening inside during training. So you can just, for example, you can send all of X in, but you can just block certain certain entries from being multiplied in here, so that certain information doesn't flow. You can also have this, right? Where the nature of your augmentation you use to perform surgery on your model itself. When we talk about transformers, we will definitely be doing this, right? But you need to understand the idea here, right? The main thing that you need to understand is once you go from PCA to nonlinearities and start thinking that the real action is coming from regularization, and the really powerful way very general way of doing regularization is data augmentation, and the fact that the problem itself is entirely up to you, this gives you this freedom, right, for how to do this self-supervision and choosing these things. So masking is a way of adding noise. That's very useful. Masking has a nice interpretation of missing data. So you can deal with that missing data in different ways, including making edits into your model itself. It's important to understand, though, why this is also related to depth in the model. So it turns out, I'll just draw it again. Okay? If you try to solve this problem using single linear layer, and a single linear layer with masking, you might not do that well. You can do it. It'll work, and you will tend to learn the right kind of thing in these singular linear layers in terms of projections, but it's not quite the optimal reconstruction. Because an optimal reconstruction would take into account what exactly is being masked, which you know. But if I give you actual question marks, you can do a better job of reconstruction than just treating them as zeros. Having it be linear would force it to be treating as zeros. But you can do other things. For example, you can just project onto solve a least squares problem. If you know a subspace that you want to go to, you can always solve a least squares problem. But a least squares problem involves something transpose inverse something. It's not one linear operation, right? It's nonlinear operation. This, if I had more time, I would spend more time on it. If you want, you can watch the lectures from last semester where I did spend more time on this, but I'll just cut this kind of next level of subtlety here. I don't think we need to. It's not that important. Okay, so I wanted to sort of close with some more comments here. Hopefully you understand now the spirit of self-supervision, where it's coming from, and why it's really not just about the problem and the loss, but about kind of thinking about it in the context of regularization and the idea of purification. Like this is the I hope added value from this lecture over blogs. Okay, so but I wanted to mention one thing. We started off by saying that in your standard machine learning class, you learned two different unsupervised algorithms. PCA, which involved the SVD, but you also learned k-means. So it turns out that it's possible to think about k-means also in the context of a kind of self-supervised problem and a kind of autoencoder architecture, right? And what you need to do that is to come up with like a softer version of k-means. It's like, it won't be exactly k-means, it'll be like k-means in spirit. And it's a different kind of loss than k-means. It's still going to have basically a squared error type of loss built in, but it'll be a little bit different in what you're trying to do. And you can also take an SGD perspective on that. Right? So again, when you think about k-means as an algorithm that you've learned k-means in a way that is very much algorithmic and iterative. It has iterations, but it's not gradient descent type iterations, right? You take some data, you pick some cluster centers, you then say map, you have a classification step where you classify every point into a cluster, then you have a finding the mean of each cluster step, and so on. Then hopefully you saw the relationship of, hopefully you saw k-means related to expectation maximization. Did you see that with a softer version of k-means that way? Who has seen expectation maximization, elbow loss, Gaussian mixtures, stuff like this for the context of k-means? Like here's k-means, a hard version, I have a soft version that's involving Gaussian mixtures. Hopefully you've seen this. If not, it's okay, but those problems can be interpreted using the lens of gradient descent. And so you can also have clustering style things that are also done for self-supervision. And this is actually done as a way of doing training. It's kind of interesting because transformers, one can interpret partially are involving some of this more clustering-like behavior, but I don't have the time. Yeah, it's fine. Okay, so that's all I wanted to say about autoencoding and the ideas behind it. You should hopefully understand all this stuff. You've seen it on the homework. You saw the homework has masked autoencoding and straight up denoising autoencoding on it. We'll talk more about it when we talk about how we train models for transformers. And we'll also talk about it when we talk about transformer models because we'll also talk about word-to-vec, which you may or may not have seen, which is more in the clustering type philosophy. Okay, with that, I will stop. Good luck on the exam. There will not be lecture between now and the exam. I do have half an hour of office hours now. We'll start here. We'll then move over to 2:58, and then I'll end at 11 because I really think you all should see Seb Bubek's talk because it's kind of interesting titled. And he's a great guy, so. Okay.